And finally, for your project, you will need to investigate about the air pollution and making a video proposing solutions for this problem.
But teacher, why do we have to do it about that subject?
You see, Hector, the air pollution is closely linked to the Earth's climates and ecosystems globally. So it's very important to be informed about this topic. Yes, Renata.
But why is it important? Isn't like other things more of a threat?
I don't know. You tell me.
Maybe because air pollution affects our health.
That's right. Air pollution in both cities and rural areas is causing fine particulate matter, which results in strokes, heart diseases, lung cancer, acute and chronic respiratory diseases.
That sounds problematic.
Yes, Hector. And that's why you need to investigate about that. And also think about solutions. You are engineers. You need to create and solve.
Okay, thanks, teacher.
Thank you.
There are many solid and gas substances found in the air as major pollutants. Some of these are
For gases, there's the sulfur dioxide that releases from burning coal and oil, the precursors of acid rain.
Then there are oxides of nitrogen, produced mainly from combustion engines and power plants. They contribute to smoke and acid rain.
Did you know that sulfur dioxide and nitric oxide are the primary air pollutants, while ozone is a secondary pollutant? Nitrogen oxide is a primary and secondary air pollutant.
And there are also volatile organic compounds, for example, benzene, toluene, and formaldehyde, emitted from fuels, solvents, and industry, precursors of ozone.
And at last, there's carbon monoxide. It is formed by an incomplete combustion, and it is toxic because it binds strongly with hemoglobin.
There are many more examples of gases, but these are just some of them. There are more of solids, and these are some examples of them.
Metals released from industry, smelting, and combustion of fossil fuels.
Transition metal oxides found in particulate emissions from oil and coal combustions.
Carbonaceous particles generated from incomplete combustion of fossil fuels and biomass.
Also, dust and inorganic salts are secondary particles formed from gaseous precursors.
So now let's see. I want you to tell me the Lewis structure, molecular geometry, polarity, and the intermolecular forces of these gases.
Our first molecule is sulfur dioxide, and we're gonna arrange the valence electrons we have in total. So we have to fulfill the octet rule for oxygen, and to make it more stable, we use double bonds. So what we get is a bent or angular geometry molecule, and it's gonna have a net polar, which has dispersion forces, dipole-dipole, but no hydrogen bond. For nitrogen dioxide, we have to fulfill the octet rule for both elements, so we're just gonna arrange them in a double bond and a single bond. And what we get is a bent or angular geometry molecule. We have a dispersion force and dipole-dipole. For carbon dioxide, we have two elements that have to fulfill the octet rule, so we just arrange it in a double bond, and we have a linear geometry molecule, which only has dispersion forces. For methane, we just arrange the hydrogens around the carbon, and we get a tetrahedron molecular geometry, which is nonpolar and only has dispersion forces. Now for methyl chloride, we will arrange them around the carbon, and we're gonna have a tetrahedron molecular structure, which is going to be polar towards the chlorine, and we have a dispersion forces, dipole-dipole, and also a hydrogen bond within the carbon.
When nitrogen oxides and sulfur oxides mix with rainwater, they form nitric acid and sulfuric acid respectively, which are in a liquid state within the precipitation. This phenomenon is known as acid rain, a form of wet acidic deposition that falls to earth in rain, snow, fog, or dust.
At pure concentration in SCP, the nitric acid has a boiling point of 83 degrees Celsius or 356.15 Kelvin, and a viscosity of 1.3 millipascals per second. And sulfuric acid has a boiling point of 337 degrees Celsius or 610.15 Kelvin, and a viscosity of between 25 and 30 millipascals per second.
Knowing this, it is safe to say that sulfuric acid has a higher boiling point and viscosity because of the stronger hydrogen bonding.
Sulfuric acid has two OH groups per molecule, which allows it to form multiple H bonds between other molecules. As it has more hydrogen bonds, it is more difficult to tear the molecule apart, which means that we need a lot of more energy to separate it.
Let's see. Milena, yeah. Pass to the board and tell me the Lewis structure and the intermolecular interaction between the acid rain and water.
So, since these are both polar molecules, they can interact with water as it's polar too, and they can form hydrogen bonds with their oxygens, so they can interact with each other.
Great job, Milena. Okay, you found about some solid particles, but what crystalline structure do they have? Do some of them have allotropic structures?
But teacher,
Yes,
what is
Renata.
a crystalline structure?
Oh, that's a good question, Renata. A crystalline structure is the ordered arrangement of atoms, ions, or molecules in a solid. In crystals, particles repeat in a 3D geometric pattern, and can be a cubic, hexagonal, tetragonal, trigonal, etc. Yes, Milena.
And what's allotropy?
Allotropy happens the same element can exist in different structural forms in the same physical state.
Okay, so like you mean that the atoms are the same, but they're arranged differently?
Exactly, Hector. So what solid particles did you find?
We found lead, we found nickel oxide, we found soot, and ammonium sulfate.
Excellent, Hector. Now search their crystalline structure and if they have allotropy structure as well. I will give you an example. Lead. Metallic lead crystallizes in a face-center cubic lattice at room temperature, and it does not have significant allotropes. Its only stable form under conditions is metallic Pb with FCC structure. What did you find?
Okay, so our team found that nickel oxide crystallizes in the rock cell structure, which is a cubic arrangement and does not have allotropes. It remains stable in its rock cell form.
Very good, Hector.
Well, I found about soot.
Okay, go on.
Soot is amorphous carbon, but it contains small crystalline regions, and these regions are similar to graphitic layers. Carbon has different allotropic structures, which are very famous. Its allotropes include like a diamond, graphite, graphene, fullerenes, and nanotubes.
Exactly. Soot is essentially a disordered form of the graphite allotrope.
I found out about the ammonium sulfate forms an orthorhombic crystal system at room temperature, and it has no allotropic structures. Ionic cells like ammonium sulfate does not have allotropes.
Okay, perfect.
Okay, so these are some of the physical and chemical properties of the pollutants we already mentioned. For sulfur dioxide, these are the chemical, and these are the physical properties.
Nitric oxide, these are the physical properties, and these are the chemical properties.
For the formaldehyde, there's the chemical properties and the physical properties.
Then we have carbon monoxide, chemical and physical.
Can you explain your proposal to solve this problematic?
Yeah, of course. It consists of a 3-layered project that, depending on the different intermolecular forces or physical properties they have, it filters out different particles. So the first layer, that is this one, it retains the biggest particles like soot, salts, and metals, which are the solid pollutants. This layer works only by mechanical filtration. It doesn't apply any chemical reaction. So this is the second layer. This one is made out of activated carbon that is hydrophobic, impregnated with amines. So the activated carbon captures the VCOs, and this happens because it has a surface with lots of loose spread out electrons. Because of this, the VOCs come close to the carbon, and the electron cloud on the carbon shifts a little, and creates a temporary dipole, which makes VOCs also have a temporary dipole. So these dipoles attract, and the VOCs stay trapped with the carbon. And finally, this is the last stage, and that one consists of a biomodule formed of microalgae that traps CO2 and liberates O2. And our project is named EcoBreathe, as you can see. By making this project, we got through some challenges. For example, some of the pollutants we wanted to filter out, we investigated how to do it, and other companies and other projects did way more complicated things that we had to do. So we actually applied what we learned in the class about intermolecular interactions to come up with our own idea. So I did like this activity.
In my opinion, I conclude that this activity helps us to encourage to create a better environment for future generations. Science. We use the theoretical part and apply it to a practical part.
In conclusion, pollution is a problem that affects us all and comes from different sources, as we saw in this video. So that's why, using the knowledge of this chemistry course, we try to find the most sustainable solution for this problem.
In conclusion, trying to find a solution to help the environment doesn't just involve wanting to, but also understanding what's happening and where the problem originates. This is something I learned during this video. Understanding that is the first step in making that change.